Okay, so I'm going to explain definition of derivative. Um, and before we do that, let's explain the little concepts that you have to know in order to understand the overall definition. All right, and each one of these aren't too complicated. Um, okay, so first one is this idea that if you have, there's kind of two concepts in this one. So let's say you, whatever this length is, so let's say this starts at 2 up here and goes until 12. Okay, so that means this whole length is 12 minus 2, which is 10. So the length of this would be 10. Okay, and then let's say you want to split this up, this whole length, into equal parts. So let's say you want to split it up into 5 equal parts, and we want to know what's going to be the length of each part when you split it up into 5 equal parts. So you'll take the entire length, divide it by the number of ways you want to split it up into equal parts. You want to split it up into 5 equal parts, and when you divide it, that gets you the length of each part. Okay, so the total length, so this is 10. You want to split it up into 5 parts, so divide by 5, and that gets you the length of each part, which is 2. Okay, so next concept is, let's say this length here, and the second one, let's say that length is 2. And then let's say this is a number line, and the x coordinate down here, we'll start out with, let's just say it's 7. Okay, so if this x coordinate's 7 and this length here is 2, you just add them and you get the next x coordinate. And that goes for no matter what you make the x coordinate or the length. Okay, so let's say this length up here is something a little weird, maybe square root 3. Okay, so if this is 4 down here, so this x coordinate's 4, this distance here is root 3. So this next distance will be 4 plus root 3. Okay, so all it's saying is whatever the starting point is, you add the distance and you get the next x coordinate. All right, and then the last one is just the area of a rectangle. So whatever the width is and whatever the length is, you just multiply length times width. That gets you the area. Okay, so each one of these you knew even before, but just to kind of get us in the right frame of mind and to the little sub skills that you have to pay attention to get the overall definition. Okay, so now let's look at some random function. We'll call it f of x here. Okay, so that's just this curve. And let's say we want to find all this area that's under the curve. Okay, and we're going to first estimate the area by making a bunch of what's called subintervals. So we have this whole length here is going to be our interval, and we're going to split it up into a certain number of these little subintervals. And in each subinterval, we're going to put a rectangle, and we're going to find the area of all the rectangles and all the subintervals. One rectangle per subinterval. Add up all the areas of all the rectangles, and that'll estimate the area between the curve and the x-axis. So that's what all this area is, always between the curve and the x-axis. Okay, so let's say we come down here and we call this A. Let's say this first x value down here is A. Oops. Okay, and then let's say the last x value of this interval is B. Okay, so we want to find the area between the function f of x and the x-axis from a to b. Okay, so all this area that's shaded, that's the area we're interested in. And the way you denote it in calculus is you put a little integral symbol. The x value farthest to the left will be the lower limit. It's called the lower limit. And the x value that's farthest to the right is called the upper limit. And then we'll have this f of x dx. Okay, so this just represents the interval that you're integrating over, which is really just the integral that you're trying to find the area of between this function and the x-axis. This little dx we won't worry about too much for now. Just represents the variable that you're integrating with respect to. But for now, this function is going to be in terms of x, and we'll be integrating with respect to x, and so that's kind of normal. Okay, but this whole area is denoted by this little notation right here. So that's what we're really trying to find, ultimately. Okay, so we've got this interval from a to b, and we want to, let's say that there's going to be like n of these little n rectangles. Okay, so if there's n rectangles, then this is the first rectangle, this is the second rectangle, this is the third rectangle. Okay, and then we're going to kind of dot here, and we're going to kind of skip ahead to what we'll call the kth rectangle, and then again we'll dot until we get to the n minus 1 and minus first rectangle, and then the nth rectangle. Okay, so now we can see there's n rectangles. We'll list out the first three, dot. Here's some kind of random rectangle in the middle that we'll call the kth. And technically the kth could be the first or the last, could be any of these, but we'll kind of denote this as the kth rectangle. And then you have the last one is the nth rectangle, since there's n of them, and then the one before it would be n minus 1, just one less. Okay, so we want to start to be able to first we want to look at maybe what's the width of each of these rectangles. So if this whole interval goes from a to b, then the length of this whole interval is b minus a. And if there's n rectangles, then if we divide this by n, we'll get the width of each rectangle. And we'll denote the width of each rectangle as delta x. So that's the change in x. Okay, so each of these rectangles, the width is b minus a over n. Okay, so now think about this. So this width here of this little rectangle is b minus a over n. The width of the next rectangle, same thing, b minus a over n. Next one, same thing, b minus a over n. Okay. So here this first x value is a, and we're going to add b minus a over n to get the next x value. So the next x value is just going to be a plus b minus a over n. Okay, so that's this x value right there. Okay, let's get the next x value. So let's say we start at a again. That means we have to add b minus a over n twice to a to get to this x value. Once, twice. So this next x value is going to be a plus 2 times b minus a over n. Okay, same idea. The next one is going to be a plus 3 times b minus a over n. Okay, if we keep going, dot, dot, dot. Okay, to the kth. This is the kth rectangle. So we're going to add a plus k times b minus a over n. So that'll give us that x value on the right hand side. Okay, and then look at the last x value. We know it's b, whatever b is, but we could also see that if we're going to add, we know that there's n of these b minus a over n's that we have to add to get to this last x value. So if we look at this, if we do a plus n times b minus a over n, this is a plus, and you can see like these n's cancel out. That's a plus b minus a, and we can see that now even those a's cancel and we just get b, which is what we would expect. Okay, so yeah, so that makes sense. If you start with a and add b minus a over n times, we get to b, just like we should. Okay, so let's start adding these areas up like we need to. Okay, so next thing is to think about just the area. Let's look at the area of the first rectangle. So we're going to use the height. So here's like this subinterval down here. Oops. So this is the width of this rectangle, the width of this subinterval, and we're going to use whatever this x value is. In this case, a plus b minus a over n. We're going to plug that into the function to get the height of this rectangle. So this point up here, the y value is a plus b minus a, or is f of, actually I'll write that. So this point here, the y value of this, so this whole point is a plus b minus a over n, comma, f of a plus b minus a over n. Okay, and that's this point right here. Okay, this is the x value, and the y value is just whatever you get when you plug it in. I need another parenthesis. Yeah, just whatever you get for this x value, you plug it in the function, and that's the y value. So that's what that point is. Okay, so it makes sense that the area of this will be b minus a over n, that's this length here, times f of a plus b minus a over n, because that's this y value. And you know, to get a distance from the x-axis up, it's just whatever the value of the function is. Okay, so the area of the first one is going to be the width. Actually, I'll do the height first. F of a plus b minus a over n, and then times b minus a over n. I'll put that in parentheses. Okay, so that's the area of the first rectangle. Okay, this is rectangle number 1. Okay, let's add it to the area of the next rectangle. Okay, so the height of this next rectangle is going to be whatever the function is at this x value. So the next x value is a plus 2 times b minus a over n, so we'll plug that into the function to get the height. And then the width is still just b minus a over n, so that won't change. So now we'll do f times, or f of a plus 2 times b minus a over n, and then times that again by b minus a over n. Okay, so notice we can kind of just keep doing that, plus dot dot dot, and then we'll go until the very last this very last rectangle. And so we know that we'll do the height is really going to be f of a plus n times b minus a over n times b minus a over n. Okay, and we know that this inside part here is really just b, but I'm going to keep it like this just because it'll make sense for the next one. Okay, so notice, look at the only thing that's changing. There's really not much changing in each of these expressions. It's almost the same thing every time. So notice the only thing that's changing is here there's like a 1 here. In the next case, there's a 2 here, dot, 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 and then we get all the way to the n here. So notice that's the only thing that's changing in each of these expressions. And so this is like perfectly set up that we can turn this into, kind of condense this into a summation. So we're just going to express this exact same thing in summation form. Okay, so when you do a summation, so the thing that's changing is called the index. Sometimes it's I, sometimes it's k, sometimes it's n. I'm going to use k, I think it's most common. And we want to go, the only thing that's changing in every case is this value, and this value goes from 1 to n. And that's what our summation will go from 1 to n. Okay, and then we'll write our expression f of a plus, and we'll put a k here, times, put that in parentheses there, b minus a over n, and then b minus a over n on the outside. Okay, and then the way summations work is, this is the lower limit, this is the upper limit of the summation, and you'll plug in the lower limit, and then plus, and then plug in every number up until you get to every whole number up until you get to n, and that's what this is up here. Okay, so we'll plug in 1 plus, plug in 2 plus, dot, 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 plug in n, and then that'll give us the area of the last triangle, rectangle. And just notice, just to kind of remind what all these are. So each one of these is the area of a certain rectangle. This is the area of the first rectangle, the second rectangle, the last rectangle, which is the nth rectangle. Okay, so that's what this expression represents, but this isn't the exact area. So notice, even if we look at this, no matter what, there's going to be a little area either above or below that we're, so that the area of the rectangle is going to either overestimate or underestimate the area, the actual area that's in that subinterval. So this is not the exact area yet. But if the number of rectangles goes to infinity, then this becomes the exact area, or approaches the exact area, because we'll use limits. So if we want the exact area, so we know the expression for the exact area is the integral from a to b f of x dx. And then we just had our method. So we're going to take this and look at when n goes to infinity. So we'll do limit as n approaches infinity of f, or of the summation, k equals 1 to infinity, f of a plus k times b minus a over n, and then times that by b minus a over n. Okay, so this is the definition of this right here, is the definition of a definite integral. So this is the shorthand notation. This is how we construct it, or at least one way to construct it. There's actually different ways to do this besides just using rectangles. And then notice kind of just one little thing, one more little thing. Notice that I use the right-hand endpoint in each of these subintervals. I use the right-hand endpoint to plug into the function to get the height of that rectangle, but you don't have to. You could technically use any point in each of these subintervals. You could use the right-hand endpoint, the left-hand endpoint, the midpoint. You could technically use just a random point in each subinterval, but you have to be systematic. So good to use right or left or midpoint, something like that. But the math works out the easiest if you use the right-hand endpoint, usually at least. All right, so that's it. So this is the definition down here. Okay, and then I'm going to do a couple problems, the first three problems, because even when you know this and you understand it, it's still a little tricky to do some of these problems. Okay, so that's good. Let me see. Okay, so here's the first three problems, and the next three for you to do will be really similar to these. Okay, so you can see like these, this looks like the thing that you just saw in the video before that, but still hard to see like which of these integrals is the same as this. They say which of the following definite integrals is equal to this. So technically there's an infinite number of definite integrals that could represent this. But there's like a few things to keep in mind that'll be typical. So anytime you see a k, you're going to have an x. That's actually always the case. So the fact that we see two k's in here means that there's going to be two x's in our expression. So you can eliminate a and c right away because those each just have one x. But notice like b and d each have two x's. Okay, now this expression out here that doesn't have a k, that's something over n. This is the b minus a over n. Okay, so that means that since it's b minus a over n, this expression, that means that the first thing to see, I think, is that b minus a has to equal 5, right? Because that's b minus a over n, so b minus a has to be 5. Okay. Usually, this number here will be a, but doesn't always have to be, and it's not in this case. So this is kind of like a little different one. So this expression here really represents what b minus a over n, like okay, so this one's a little different maybe, but so really a is going to be 0 because the a plus, in the video before, that little expression a plus k times b minus a over n, here the k comes second, it's really a plus b minus a over n times k, how they're writing it. So if you compare it, this to this, you would think that this a would be 1, but this, if a was 1, this is the expression that you'd be plugging in for every x. Anywhere where you see an x, you'd have to plug this in. And the fact that this expression has a k, that means this is something that got plugged in for an x, and there's no plus, anything plus here. There's just an expression. So here, I'll show you. This is kind of confusing. So let's say we're going to say a is 0, and we know that b minus, so we're going to say a is 0. And if a is 0 and b minus a over, is 5, that means b has to be 5. So those would be our limits, and we're going to kind of test it, see if that's right. Okay, so if that's right, that means our integral has to go from 0 to 5, because it always goes from a to b. And then b minus a over n, you know, or a plus b minus a over n would be 0 plus, or times k, would be 0 plus 5 over n times k, 5k over n. Okay, so that's what's going to get plugged in for every x. So in order to get this expression, you have to do 2 times this. So this is this expression, this part here, 10k over n, really represents a 2x. So notice if you plug 5k over n for x here, you get 10k over n. Okay, this expression out here is really kind of our dx. It's the width, but we won't worry about that. Okay, and then now if we're saying that this is what we plug in for every x, that means this just has to be x, since this is the exact same thing, which would make this inside just 1 plus x. And when we just look to see if that's an answer choice, which it is, and that's D. Okay, so you can see, you know, little tricky, but notice there's like little things to keep in mind. You know, anywhere where you see a k, there's got to be an x there. The b minus a over n times, you know, a plus b minus a over n times k is what you plug in for every x. So yeah, so here, let's look at the next one. Okay, they say, which of the following definite integrals are equal to that limit sum definition? Okay, so, you know, like before, we were saying that there's an infinite number of ways to represent a definite integral according to this limit sum definition part. So any one of these could be an answer, but let's see. Okay, so the first one. So almost always easiest to start out with the integral and then test it and see if we get this limit sum definition. Okay, so we can see right away for number 1 that a is -1 and b is 4. Those are the limits. So that means our b minus a over n is 5 over n. Okay. And then the thing that we're plugging in for every x value is a plus b minus a times k over n. That's what we're plugging in for every x value. Here we have this 1x value, just sine x. And for us, this is going to be -1 plus 5k over n. Okay, so this is what we would have to plug in for every x value. So let's see if it works out. So if we plug this in for this x, we get sine of -1 plus 5k over n, so that checks out. And then we have just b minus a over n on the outside, so that checks out. So the first one, that checks out. Okay, let's look at the second one. Okay, so the lower limit 0, the upper limit is 5. So that means a is 0 and b is 5. Okay, so that means that b minus a over n, same as before, 5 over n. Okay, so that checks out. We should have a 5 over n on the outside, so that's good. Okay, and then here our a is 0, so if we do a plus b b minus a over n times k. If a is 0, we get 0 plus, so we just get b minus a over n, which is 5 over n times k. Okay, so this is what we're going to be plugging in for every x value. So let's see. So if you take 5k over n and plug it in for this x, you do get negative 1 plus 5k over n, like up here. And then the outside just should be 5 over n, which is just b minus a over n. So that one checks out also. Okay, so let's look at the third one. Okay, and the third one, the lower limit is 1, and the upper limit, or sorry, the lower limit is 0, and the upper limit is 1, so a is 0, b is 1. Okay, if we do b minus a over n, we get 1 over m. Okay, but notice we have this 5 on the outside, and this 5 can come in here. Okay, so this 5, we could multiply it by this, by 1 over n, to get 5 over n, like we want. So if we take this and do 1 over n times that 5 that's on the outside, we do get 5 over n, like we need. That's okay. Okay, and then now a plus, for us, the a plus b minus a over n times k is 0 plus, and then this is really 1 over n times k, so really just k over n. Okay, and that means this is what we're plugging in for every x inside of our integral. Okay, so let's see. So this inside part, or this k over n, needs to be put in for this x, and then we get 5k over n, and that's perfect. So that means this whole, when we substitute this k over n, when we substitute it in for x here, we get negative 1 plus 5k over n, just like we should here. Okay, on the outside, we would technically get a 1 over n, but that means we can multiply this 5 by the 1 over n to get this 5 over n, like we should, and so that checks out. So this part we would get, and then this part on the outside we would get, and so all three of these check out. So that means D is our answer. Okay, so this is, a little strange one, but just this one's just showing you that whatever the limit sum definition of definite integral looks like, there's an infinite number of ways to represent it. So they're just kind of making you see that. Okay, now they say, which of the following is a left Riemann sum approximation of that with n subintervals of equal length? Okay, so when we did it, the thing that we're plugging in for x, when we did the right hand, when I explained the definition, I used the right Riemann sum. Use the right hand endpoint in each subinterval to plug into the function to get the height of that rectangle. But you could use the left hand endpoint in each subinterval to plug into the function to get the height of the rectangle in that subinterval. The only thing is, the thing that you'd be substituting for x, instead of a plus b minus a over n times k, this is what you'd use for the right hand endpoint. You'd have to do k minus 1. Okay, and I'm not going to explain that too much here. I'll explain it in class if we need to. Okay, so now this is the expression that we're plugging in for every x in here to get our limit sum definition. Okay, so if we're going to start out with this definite integral, we know exactly what a and b are. So in this case, a is 2 and b is 8. Okay, so we can substitute it into here. So if a is 2, that'll be 2 plus and then b minus a is 6. So 6 times k minus 1 all over n. So this is what we're going to be plugging in for this x right here. Okay, so notice if we substitute this in for x, okay, and we'll now go to the limit sum definition. And actually, they say what's the left Riemann sum approximation, and so all these answers are approximations because they don't have the limit as n approaches infinity on the outside. Okay, so we just have the summation. Okay, we know that our function here is cosine. So we have cosine of, and then we know that we're going to be plugging this in for that x, which means we're going to be plugging it in and squaring it. So take plus 6. And then squaring that. Okay, and then we always have to have our b minus a over n on the outside. Since b is 8 and a is 2, we'll have a 6 over n on the outside. Okay, and then we look at our answer choices, and that's C exactly. So that's our answer. Okay, so, a little tricky, a little complicated. But notice if you just kind of keep a couple things in mind, it makes it easier. And then with practice, like anything, this will be a little easier. Yeah, so just notice this a plus b minus a over n times k, or k minus 1, depending on if you're using RRAM or LRAM. And just to kind of remind, this is what you'll use if you're using LRAM with the k minus 1. If we were using RRAM, we would just use k instead of k minus 1. Whoops. Okay, so yeah, so try to do the other 3 problems. Pretty similar to these, definitely in format, and pretty similar otherwise. All right, good luck.